The purpose of this video is to discuss evaluation of contour integrals using the parameterization method. This is perhaps the most straightforward method to evaluate a contour integral, but it's one that we'll only use initially. So let's suppose that gamma is a smooth curve in some region D of the complex plane. We'll assume that f is defined on D, and we're going to assume that gamma has a parameterization, which we write gamma colon z of t, where z of t is a function of t where t varies between a and b. And so the idea is that as t varies between a and b, thinking about t as time, z of t is going to trace out a curve in the complex plane. Then the parameterization method states that to evaluate the contour integral of f along gamma, we can evaluate the integral from t equals a to t equals b of f of z of t times z prime of t. So that means to evaluate this contour integral, we need to do the following. First, we construct a parameterization of gamma, namely z of t, where t varies between a and b. And we're going to focus on parameterizations of circles and line segments in this video. Then we're going to substitute our formula for z of t into the function f and simplify if possible. We're going to calculate z prime of t. We're going to multiply f of z of t and z prime of t, which we've computed in 2 and 3, and we're going to simplify the results really as much as possible and integrate from t equals a to t equals b. Now, proof of this result can be found in various places, including Saff and Snyder's text, specifically Theorem 4 from section 4.2. Now, this is perhaps one of the most straightforward means of evaluating contour integrals, but we will discover soon that there are easier methods. So let's take a look at an example. Let's evaluate the contour integral e to the z, where gamma is a segment in the complex plane that starts at the point I minus 1 and ends at the point 2 plus I. In other words, minus 1 plus I, which is over here in the complex plane, 2 plus I, which is over here in the complex plane, and we're going to evaluate on the line integral starting here and ending there. So our first step is to find a parameterization of that line segment. The standard means of determining the parameterization of a line segment is to take the parameter 1 minus t, multiply it by your starting point, plus t times your end point. So 1 minus t times I minus 1 plus t times 2 plus I. And this assumes that t varies between 0 and 1. So for example, if t is 0, this goes away, and we have 1 times I minus 1. That's our starting point at t equals 0. If t equals 1, this all goes away, and we're left with 2 plus I. That's our ending point. Now we're going to also need z prime of t, and if we calculate the derivative of this with respect to t, we simply get 3. So, next step. Take our formula for z of t, substitute it into f, which in our case is the exponential function. So we get e to the minus 1 plus I plus 3t. And I'm going to simplify this a little bit. E to the minus 1 plus I times e to the 3t. So we're going to take f of z of t, and which is this, and we're going to multiply it by z prime of t, which is 3, and then we're going to integrate this with respect to t from t equals 0 to t equals 1. And again, the reason we choose 0 and 1 is because those are the starting and ending points of our bounds on t. Now the first thing I would do is I would take this constant outside the integral. If I compute the antiderivative of e to the 3t times 3, that's simply e to the 3t. So I now evaluate that at t equals 0 and t equals 1. That will give me e to the third minus e to the 0, which is 1. So that's the value of our contour integral. Of course, we could simplify that a little bit, but let's just leave it like that. Let's take a look at an example where we're dealing with something circular in nature. Specifically, let's evaluate the integral of z squared, where gamma is the right half of the portion of the positively oriented circle of radius 2 centered at 1 plus I, which starts at 1 minus I and ends at 1 plus 3I. So here we have I have a picture in the complex plane. Here's the real axis. Here's the imaginary axis. The origin is right here. So here's my center at, that's the point 1 plus I. And I'm going to start at 1 minus I, which is down here. And my circle is going to be, arc is going to be positively oriented, and it's going to end up here at the point 1 plus 3I. This may look a little off to you because the origin is back here. It's not right there. So the first thing we need to do is we need to come up with a parameterization of this arc. This arc is part of a circle. It's part of a circle centered at this point of radius 2. And we know how to parameterize such a circle. It's given by the center, which is 1 plus I, plus our radius times e to the it. Now in our case, usually we would go from t equals 0 to t equals 2 pi. That would trace out the entire circle. We only want the circle going from this part up to this part. Down here, t is minus pi over 2, and up here, t is pi over 2. We don't say 3 pi over 2 because we want to go from negative pi over 2 to pi over 2. We want to go from a smaller value of t to a larger value of t. So that's our parameterization, 1 plus I plus 2 e to the it, where t varies between minus pi over 2 and pi over 2. The derivative of z is 2I e to the it. Now we need to take our z of t and we need to substitute it into f, which was z squared. So here's my 1 plus I plus 2 e to the it. I'm going to expand that and simplify, and this is what I get. You may want to pause the video for just a moment to check that this is indeed the case. We're going to take our f of z of t and we're going to multiply it by our z prime of t. Doing so, I get this expression right here. Again, you might want to pause the video just to verify that this is the case. Now we're going to take this and we're going to integrate it from t equals 0 to from t equals minus pi over 2 to t equals pi over 2. Okay, so here's what we have. Now, I'm going to take this integral and I'm going to split it into the sum of 3 integrals, minus 4 e to the it, this portion, and this portion. Let's handle each of these separately. So the antiderivative of minus 4 e to the it would be minus 4 divided by I e to the it. Now, dividing by I is the same as multiplying by negative I. So in other words, if I take this minus 4 and divide it by I, it simplifies to be just 4I. So the antiderivative of that term is 4I e to the it. We're going to have to evaluate that at pi over 2 and minus pi over 2 and subtract. This is a constant, which I can factor outside the integral. Then we're going to integrate 2I e to the 2it dt from minus pi over 2 to pi over 2. And similarly, 8I is a constant I can pull outside of this other integral. Now, let's take e to the it and substitute in these endpoints. Here's where we're going to have to use the unit circle. If t is pi over 2, I have e to the I pi over 2, which is up here on the unit circle on the complex plane. That corresponds to I. So when I substitute pi over 2 into this, e to the I pi over 2 is I. When I substitute minus pi over 2 in here, I get e to the I minus pi over 2, which is down here on the unit circle. That's minus I. So the result of substituting the endpoints in here is I minus a minus I, which is, this is going to be minus 2I. Minus 2I times 4I is minus 8. Let's take a look at this second integral. The antiderivative of e to the 2it is e to the 2it over 2I. and I'm going to substitute my endpoints and subtract in just a moment. The antiderivative of e to the 3it is 1 over 3I times e to the 3it. But when I divide by 3I, 8I over 3I is going to give me 8/3. Okay, so we've seen that this quantity simplifies to be minus 8. Dividing by 2I is the same as multiplying by 1/2 times negative I. So if I take 1/8 times 1/2 of negative I get minus 4I. If I take minus 8I over 2I, I get minus 4. Again, we are using the fact that when you divide by I, it's the same as multiplying by negative I. Now we're going to, this quantity then, this portion simplifies to be what we have in front. We're going to take e to the 2it and substitute our endpoints in and subtract. When I substitute pi over 2 in here, I'm going to get, because the 2's are going to cancel, I'm going to get e to the pi I. And the same thing is going to happen when I substitute minus pi over 2. I'll get e to the minus pi I. So e to the pi I on the unit circle is 1. E to the minus pi I is, e to the pi I is negative 1, and e to the minus pi I is negative 1 as well. So I'll have minus 1 minus a minus 1, which is going to go away because this is going to be 0. So I'm going to have the minus 8 plus all of this, which is just 0. Now I need to contend with this last term over here, 8/3. If I substitute pi over 2 in, I get e to the 3 pi I over 2. Substituting minus pi over 2 in, I get e to the minus 3 pi I over 2. Now on the unit circle, e to the 3 pi I over 2 is negative I. And e to the negative 3 pi I over 2 is I. So I'm going to have, this is minus I, this term right here without the minus sign is I, so this is going to be minus 2I. So 8/3 times minus 2I is minus 16/3 I. So that means the final value for the integral of f of z along that circular arc is minus 8 minus 16/3 I. Here are a few examples for you to do in preparation for class. Use the parameterization method to evaluate each of the following: the integral of z minus I squared, where gamma is the positively oriented circle of radius 3 centered at I. You should see that you get a nice answer. F of z equals z squared. We want to integrate that along gamma, where gamma is the line segment starting at minus 1 and ending at I. And then the integral of z bar, where gamma is the top half of the unit circle starting top half of the unit circle starting at z equals 1 and ending at z equals minus 1. Now remember that the conjugate function leaves the real part alone and takes minus the imaginary part times I. So just to recall what the conjugate function is. So do these three in preparation for class.